And welcome back to topic 4, radical functions. Today we are looking at the square root as a function transformation. Now when we look at something like that, we'll be given a graph of f of x, or perhaps an expression that is equal to f of x, and we'll be involving a square root of f of x somewhere. Worth noting is that that square root is outside of these functional brackets. It's not part of the input for f, so it's not going to be a horizontal effect. It will be vertical, right, because it is outside those brackety do's. So this is going to affect strictly our y values. Any vertical transformation will. We're going to look at a couple of cases, a couple linear cases, and then we're going to discuss where f of x is defined in each case. We'll talk about what we expect to see, and we'll go from there. So I've got the graphs of y equals x and y equals half x minus 2 done here already, things that you should be able to do already. And then we'll graph y equals the square root of that function and take it from there. Feel free to pause if you want to try it. I am diving in. So if we're going in here, we're saying y equals the square root of f of x. Somewhere over here, whoop, that's an eraser, that's great. Somewhere over here, where y is 0, well, the square root of y, the square root of f of x would be 0. Somewhere over here, where f of x is equal to 1, we're taking the square root of f of x. The square root of f of x is 1. Here, f of x is 2. Square root of f of x is the square root of 2, which I guess is like 1.4-ish, but I don't really want to pursue that. The next one I can get nicely is over here, where f of x is equal to 4. So the square root of f of x is 2. Really, what we are graphing here is just straight up y equals the square root of x. And that's because we're doing y equals, the square root of f of x, where f of x is just x. So we should get that same function back. And then where's 4, 5, 6, 7, 8, noof. I think 2, 3, 4, 5, 6, 7, 8, 9, perfect. So that's where we get our other one. And then we play connect the dots. Now, something else worth noting is that when you take the square root of a function, it's higher than the original between 0 and 1, between y values of 0 and 1, but then it goes lower after that. So the square root of 0.5 is actually more than 0.5. To feel, dig. It has that parabolic shape, just kind of tipped over. That's that one all done. So things we notice. Where is f of x defined? Well, first of all, I guess I didn't really talk about what are the square roots of these, but we know that we can't take the square root of any negative number. So square root of f of x is only defined wherever f of x is at least 0. That's that one done. Super duper. All right, try this other one. I dare you. Wow. I've got the graph of y equals half x minus 2 there, so graph y equals root of f of x. Well, I'm assuming you paused. I'm jumping in. Square root of 0 is 0. Square root of 1 is 1. Square root of 4 is 2. So we're just remapping y values for each of these x values. And then, of course, connect the dots. In this region, will be greater than the original curve, the original line. And then in this region, will be under it. So there's our graph of y equals root of f of x. So in both these examples, there were points that straight up didn't change. So they were common to both f of x and root of f of x. And the question is, why did this occur? Worth examining. Let's check it out. This is different, but these are same. Similarly over here, this is different, but these are same. So why is that happening? Why do those points not change? Didn't we just transform this whole thing? Shouldn't everything be different? No! Not always. What we have here are invariant points, which I guess is a definition for on the next page. But this point where y equals 0 didn't change because the square root of 0 was 0. This point where y equals 1 didn't change because the square root of 1 is 1. So where did that happen? You're right, I should be saying f of x, not y. And why does that happen? Because of that. So this leads us to our definition of invariant points, which is here. So it's a point that, when you transform it, remains unchanged. And you would have talked about that last year with reciprocal functions. Essentially, this is any point where x, y gets mapped to the same x, y point. So those values remain completely unchanged. And for the square root of a function, as was mentioned above, that happens where y equals 0 and y equals 1. So if you're going to graph the square root of a function, you probably want to start by actually plotting those invariant points, assuming they exist. So if you have parts where y equals 0 or y equals 1, just put a dot right on that spot. And then after that, if you have square numbers for y values, then you should be able to plot the square roots of that. Some notes about domain and range. So domain-wise, maybe f of x has infinite domain, maybe it doesn't. But the domain of the square root of f of x, well, that will only be the collection of points, or the collection of x values for which y is at least 0. So over here, domain of square root of f of x was only everything that was non-negative for x. Over here, it was only everything greater than or equal to 4. And that's because it was after that point that f of x was non-negative. Range-wise, it's interesting. So the lowest value of f of x, the square root of that, will be your lowest bound on your range. Assuming that, how do you say, unless f of x takes on negative values. So I guess the lowest non-negative value is the square root of that is your lower bound for the range. And then the higher bound for f of x, the higher end of its range, the square root of that is your higher end of the interval for the range of f of x. So we're going to try these two real quick. We'll graph the square root of each function. We'll state its domain and range. Okay. Well, I'm jumping in. Of course, you're pausing and trying it yourself. I'm going to go in here. I'm going to put a 0 right there. That was probably meant to be put right on the lattice point, but whatever. putting a point right there because square root of 0 is 0. Putting a point right here because the square root of 1 is 1. And over here, y is 4, and the square root of 4 is 2. And that's enough to get me to graph this thing. And remembering that over here, I should be more than the original function, and elsewhere beneath. Notice I'm doing like a sketchy progression. I'm not just drawing this in one swoop. Remember, we should draw our graphs almost as if we care about how they look. What a world that would be. So this is our graph of y equals the root of f of x. Domain of this thing. Our lowest domain value, our lowest x value is -1. And then this goes on forever, ever, amen. So we're heading off to infinity. Range-wise, our lowest non-negative y value was 0. So we're bounded by 0. Our highest non-negative y value, well, this thing went on forever, ever, to infinity. Square root of that. Oh. Yeah, I'll take it. It's infinity. Oh, look, another one. Again, I start by putting my zeros. For this, you can assume that this was meant to be on a lattice point. My apologies for the poor Microsoft Word skills. I will improve. And there's ones. And then we graph this thing. We're above the curve on one side. And then we beneath it elsewhere. Actually, it probably is a bit different from that. Not very much, but like, I'm willing to bet it's like that. And then we get my other side. And that's that. Hooray. Domain. Whoa! It's a couple of segments. You can phrase it a couple of ways. My preference is still interval notation. So leftwise goes as far as negative infinity. Ooh, that's a nice infinity. And then we stop here hard at -3. And then we've also got this chunk over here. So you can use your union symbol. That looks suspiciously like a U. And we go from 3 to positive infinity. If you prefer set notation, we could say that's the set of all x such that x is less than or equal to -3, or x is greater than or equal to +3. And it's a real number somewhere in that span. You don't have to, but like choose your preference. As long as you're correct, you're correct. Either notation is fine. And just to say that again, because I know someone's going to ask me this. Either notation is fine. Range. We're going to take this as low as 0, and it goes on infinitely. That one is done. If you, I guess if you want to have that in set notation, then you're good. That's that. There is some practice work hereabouts, so give that a try. Give it a spin, give it a go, give it a shot, give it a whirl. Enjoy it because it's math, and math is always enjoyable, as we all know. And as always, if you have any questions, please let me know somehow. Via Teams, in class, in person. Send me a fax to the school's fax line. Mail a letter. But whatever you need to do, just make sure you do it. There's only one section left in this topic, so have fun with that. We're zooming through this thing. Miss you all till I see you again. Goodbye.